Hey folks, we are back, section 3.33, talking about a really cool concept called the equivalent kernel. So kind of a different perspective on how to do regression, which I think is really going to come up a lot in chapter 6, but it's nice to kind of get a preview of it here. To kind of set up the problem, let's go back to kind of the case of the sinusoidal data. So I'm just going to make a little bit of room up here. I'm going to make some data for us to work with. So let's say this is, we're in this is X, you guys can see this is Y, very good. And let's say we've got, we've got some data points already. So like, let's say here are, our data points. Okay, so I'm just gonna, they're really quite regular, but whatever. Okay, so that's our data. And now let's say we're interested in prediction, or we're almost always interested in prediction. So we, in this regression setting, we've been going through this, getting weights and all of this, but ultimately what we're interested in is predicting kind of new values. So let's say we're interested in getting the value at this point. So at this, we want to know what is the value at that magenta value, value for X. Okay. How are we going to do that? Well, so what we've done so far is we said, okay, well, we're going to have, we've built up a series of, we know we have some basis functions. So in our case, maybe the Gaussian basis functions, and they have kind of these, sensitivities or tunings like that. And so this would be kind of, these would be our different basis functions. This would be like, so this is like phi 1 of X, phi 2 of X, etc., all the way to, phi m minus 1 of X. This is X, this is the value. And what we've done is we've figured out some weighting of the value of these features to tell us, that would give us the new mean. So, for this particular value of X, I guess maybe like this feature would be really maybe kind of active. So we would get a value there, maybe a value here, and probably the rest of the features are not active. And we have some weights that we apply to all of the feature values. So let's actually just put them all in. So I guess this particular feature would be 0, that particular feature is that particular feature is that, this particular feature is 0, 0, 0. So we would do some weighting based on the regression that we've done, and we would say, well, okay, well, y, oops, let's try it, y of x is going to equal to, let's say w2 times phi 2 of x plus w3 times phi 3 of x, and the rest would be, you would weight all the others too, but their values are 0. So that's how we would do it. We would kind of map our input into our basis, into our features, and then we would use that linear combination that we've learned from all the data to compute that. But you could say, well, like, imagine if you had like lots of this data. It kind of seems like what you should be able to do is just kind of interpolate between the points, right? You could say, well, imagine the setting where you've got, way more data, right? Like, and you've got tons of data, and I'm asking you for the value here. Like, you're pretty sure that it's going to be like sitting somewhere around there, right? Because you're like, well, there's a data point right there, and there's a data point right there, so maybe actually, sorry, I should be, somewhere up there, right? So the value should be halfway, maybe some kind of average of the values of the points the data points, the training data that we have that are near it, and maybe these points farther out shouldn't actually contribute very much. So the nearby points should contribute a lot, and the farther out points shouldn't contribute anything. And the value that we're going to report is going to be some kind of weighted average of our training data. So instead of kind of necessarily mapping into kind of into our feature vectors and then doing a linear combination of those, maybe we can just do some clever weighting of our input data to provide a prediction for new data. And what this equivalent kernel stuff is about is essentially showing that our two approaches, this doing the weightings of the basis functions, and what we just talked about, this kind of interpolation, are actually equivalent. So you can think of what we're doing when we're reporting the means and covariances, when we're doing kind of these weighted combination of features, is actually interpolating our data, and the interpolation, the way we interpolate, that's kind of determined by our basis functions. Okay, so that's what this section is about. As I said, there's going to be much more about this in chapter 6, it looks like, so we're just going to get a taste of it here. Okay, so let's get started. Okay, so it says the posterior mean solution for the linear basis function model has an interesting interpretation that we're going to be talking about, which will set the stage for kernel methods, including Gaussian processes. Okay, so if we substitute 3.53 into the expression, we see the predictive mean can be written in the form. So remember, we don't need to scroll up. Essentially, remember what we did was we had our y of x was always equal to our weights times our features, and then we found that given a particular data set, the average value of y was going to equal to the average value of the weights times those features, and that average value was m of n. And now for the particular setting that we had, where our prior, one of our priors was set to 0, this m of n was just going to be equal to s of n times phi transpose t, I believe, something like that. Let's just go have a look. Let's just have a look. Yeah, there it is, exactly. So we found that kind of the weighting, our average of the average of our weights after loading the data had this particular value, and now we're just going to plug it in. Okay, so that's what we're going to do here, and then it's going to give us an interesting interpretation. Okay, so we've plugged that in, and we get this particular value. And notice that these are kind of our data points that we've actually seen, our training data, and this is our kind of design matrix that has our features of value to our training data. And now if we take a look at it, this is the form that it takes. Okay, and you're like, well, what's so special about that? Well, you can see that actually we're predicting our mean prediction for a new data point is actually going to be a linear combination of our training data, so that's where the t of n's come in, weighted in a kind of a particular way. So and s of n was kind of the covariance of our weights, but you can think of it as also as something related to the overlap between the feature vectors. So now the mean of the predictive distribution at a point is given by a linear combination of the training set target variables, so that we can write this. So I'm going to highlight this point because it's really important. The mean of the predictive distribution is given by a linear combination of the training set variables, and that's a really cool idea. So a linear combination of the training set target variables, so that we can write y. So our mean prediction, this is the prediction evaluated as the mean of the weights, is actually just a linear combination of our exactly what we were talking about before, right? Weighting our observations by a certain amount, by this kernel, which is called the smoother matrix or the equivalent kernel, and it has this particular form. So, and one way to understand this is you can think of it as, so what are we doing here? So we're in this particular statement, for each data point, we're kind of measuring some kind of distance between the input, that particular input in the training data, and the point we're interested in. And how do we measure that? Well, how do we measure that distance? Well, we measure the similarity of the features, of the corresponding features, but kind of, let's say, modified by our covariance. So it's kind of like a distance. You can think of this as a distance. So, you're doing a dot product between two things. But there's a particular metric, there's a particular weighting of that you apply that depends on your basis function. You can go back and see what the form for that is. But effectively, it's the same idea that we had kind of intuitively, right? So you're going to weight the contribution of each of your training points by the distance to that point from the point you're interested in. And that distance is essentially related to the overlap of your features. Okay. So it says regression functions such as this, which make prediction by taking linear combinations of the training set target values, are known as linear smoothers. Note that the equivalent kernel depends on the input values x of n from the data set, because these appear in the definition of s of n, right? So s of n had our features were computed for all of our training data, and there were overlaps, and I think there was an inverse somewhere. So that's where x of n comes in. So in this particular expression, there doesn't seem to be any, like, where the training data go. Well, it's actually in there. The equivalent kernel is illustrated for the case of the Gaussian Bayesian function in figure 3.10, in which have been plotted as a function of x prime for 3 different values of x. So let's have a look at this figure. It's quite cool. So Right. So I think the way to understand what's going on. So this is let's call it x of n. And now, so on this axis is going to be x of n, and we're going to look at 3 different values of x. So we're interested in computing the prediction, where we're interested in predicting the value of of our function at 3 different points. We're going to try it at 3 different points. And what this equivalent kernel says is it gives you a weighting of your training data as a function of its location. So let's just look at this particular line, right? So we're interested in this particular case, let's say deciding the x's are going to go from -1 to 1. So let's say this particular line corresponds to, and this is -1 to 1. So let's say this is at, we're interested in k of x equals -0.5. Okay, so that's what we're interested in. Now it says the way to compute the output is to weight your data according to this particular function. And now what's special about this function? What says that data points, this is 1, this is -1, this is the point that you're interested in, -0.5. It's telling you that whatever your input data were, the ones that are like really far out don't really matter. It's just the ones that are around -0.5. Those are the ones that are going to contribute. So weight those values, those t of n's, according to this particular function. So you're actually weighting everything, but it just so happens that the rest of the weights are basically 0. If you're interested in now at k of x that equal to 0, well then what matters is the points around, the data points, the input data around 0. If you're interested in at 0.5, then what matters is the data at 0.5, and so on. And I've got some code to go with this section, and you can kind of play around with this and see kind of how it works for yourself. But that's the basic idea. This is kind of how you weight your data, your input data, to determine the value at a new point. How much emphasis you should put on all of the various points in your input data to come up to determine the value, the mean prediction at a new point. So that's I think it's a really important figure. So make sure you kind of understand what this figure is all about. And I think then you'll have a good idea of what this kernel is all about. Okay, so we see that they are localized around x. That's what it's talking about the kernel. And so the mean of the predicted distribution at x is obtained by forming a weighted combination of the target values in which data points close to x are given a higher weight than points farther removed from x. So this is kind of the crucial. They're localized around x, and the mean predicted distribution of x is obtained by forming a weighted combination of the target values. So let's highlight the important bits. A weighted combination of the target values in which data points close to x are given higher weight than points farther removed from x. So this is kind of going back to our intuition, right? So yeah, exactly. So intuitively, it seems reasonable that we should weight local evidence more strongly than distant evidence. Note that this localization property holds not only for the localized Gaussian basis functions, but also for non-local polynomial and sigmoid-based functions. So in the code example that I'll provide, you can change the basis function. You'll see that it's basically the same idea. Great. So now that was just talking about the mean value of the prediction. What about the covariance of it? So further insight into the role of the equivalent kernel can be obtained by considering the covariance between y of x and y of x prime, which is given by, so we're just going to compute the covariances, and the features are fixed. So all that matters is WWT, and its covariance is just S of n. And so we see that actually the covariance between our predictions is again proportional to this kernel. So essentially it says that nearby points are going to co-vary with each other, and farther apart points aren't going to affect each other as much. So that's all that's being said. So from the form of the equivalent kernel, we said the predictive mean at nearby points will be highly correlated, whereas for more distant points, the correlation will be smaller. Okay. Now he says, okay, so the predictive distribution is shown in 3.8. So that was, let's just have a look at which one he's talking about. That was this one. So remember, this was for single points. We're looking at single points. And the error bands were for just that point. So that was kind of the variance of single points. That would correspond to the covariance of y of x with y of x. So x prime equals x. allows us to visualize the pointwise uncertainty of prediction, so we already did that. However, by drawing samples from the posterior distribution over W, which is what we did, and plotting the corresponding model, we are visualizing the joint uncertainty in the posterior distribution between the y values of 2 or more x values as governed by the equivalent kernel. So now we know kind of how those things vary, and that's going to be determined by this equivalent kernel. So let's just highlight a few things. So the covariance of this is going to equal to that, which is pretty cool, governed by the equivalent kernel. Okay, so now he says, the formulation of linear regression in terms of a kernel function suggests an alternative approach to regression. So that's kind of what all this stuff is all about. As follows. So instead of introducing a set of basis functions, which implicitly determines an equivalent kernel, we can instead define a localized kernel directly. So you can kind of use your knowledge of what you think, how similar, how much you should, how nearby points should affect each other, and just do your regression that way. You can just kind of skip. You can kind of skip the feature step, basically, the basis function step. Although it turns out for kernels, each one of these kernels will correspond to a particular feature. So, the features are always there in the background. Instead of introducing a set of basis functions, which implicitly determines an equivalent kernel, we can instead define a localized kernel directly and use this to make predictions for new input vectors. So, we can instead define a localized and use this to make. Okay, so let's do that. A localized kernel directly and use this to make predictions. That's what we want. So instead, define the kernel itself. So this leads to a practical framework for regression and classification called Gaussian processes, which is kind of a really important topic, which was, I think, also very kind of coming up around the time this book was written, the mid 2000s basically, and it's still like really, I think I work with it a little bit. It's kind of quite a beautiful topic, and we'll learn all about it in chapter 6. Okay, we have seen the effective kernel defines the weights by which the training set target values are combined in order to make a prediction at a new value of x. Now it can be shown that these weights sum to 1. Okay, so that's kind of cool. How are we going to do this? Well, remember, what are we trying to do here? So remember, our general approach is we're weighting the data, and here this is going to be equal to y of x at the mean of our weights. So he says, well, the way you can see this sum holds is by noting the summation is equivalent to considering the predictive mean, so this thing, for a set of target data in which t of n equals 1. So all of our t of n's are equal to 1. Now, and essentially, as long as your basis function are rich enough to be able to fit that situation, so you can kind of add more basis functions, etc., as you need them, then you'll always be able to solve this, which means you'll always be able to, so for data that's equal to 1, you will be able to fit it exactly. So this will have a solution. And so that means that the sum of your kernels will be equal to 1. So provided the basis functions are linearly independent, so that they can, you can fit the data with them. There are more data points in basis functions, and that one of the basis functions is constant, corresponding to the bias parameter, then it's clear that we can fit the training data exactly. So that's this. So we can always find a solution. So the t of n's are all 1, the outputs are 1, and we can fit it. So that means that the only thing that's left is, well, just the sum of the kernels over data points at any point x. We can fit the training data exactly, and hence the predictive mean will be simply y hat of x equals 1, from which we obtain that equation. Note that the kernel function can be negative as well as positive. So although it satisfies the summation constraint, that equals the sum to 1, the corresponding predictions are not necessarily convex combinations of the training set. So all convex combinations are the ones where all of the numbers sum to 1, and they're all between 0 and 1. So that's kind of, he's just saying that, look, we are indeed summing to 1 here, but those kernels could be negative, so it's not quite a convex setting. Doesn't have to be anyway. Okay, and the last point is, and we're going to get to this in chapter 6, that the equivalent kernel satisfies the important property shared by kernel functions in general, namely that it can be expressed in the form of an inner product with respect to a vector psi of x of nonlinear functions. So, the kernel is just the idea with this is that you can think of what kernels are doing is they're taking your data and transforming it non-linearly, often into a higher dimensional setting, not always, but and then computing linear overlap in that space. So kind of the power of these kernel methods is that they allow you to kind of leverage the power and kind of the clarity of linear methods, but to do that in but while also getting the advantage of kind of non-linearity and higher dimensionality. So that's something we'll see kind of more of later. He's just saying that, look, the kernel that we have, we can actually look at what the features are, and it turns out, okay, the features have this particular form. So you can think of what the kernel is doing as projecting your data non-linearly into some other space and then computing a linear overlap there. So that's, I think, a point that we'll come back to later. You don't need to worry about it too much for now. But that's it. So I think that's about all I wanted to say about this chapter. So I think it's a really cool perspective on regression. You can think of it as kind of maybe dual to the other one of learning the weights. They're equivalent. One way you learn the weights of the basis functions. Here you equivalently can interpolate the training data that you're given. One other point that we could make is that, look, this interpolation idea is cool, but it's going to be problematic if you have lots of data points. So that might argue for using the first approach we've been using of kind of estimating the weights and then doing our prediction. But I think it's just good to know both. And finally, I wanted to just show you guys, so I've provided some code for this so you can kind of play around with it. So let me just switch over to that. Yeah, there we go. So let's go to the top of this. So yeah, so there we go. So I've got some code here that you can get some different basis functions, so Gaussian, polynomial, sigmoid, so you can kind of play around with them. We then kind of you can plot the basis functions, and then we generate some sinusoidal data, so kind of the same kind of stuff we've been working with throughout. We compute our kind of phi matrix. That's always really important. So here are the phi's. We evaluate the features on the data points. We compute the various precision matrices and covariance matrices that we need. And then we finally just compute the equivalent kernel, and you can see exactly kind of how we do it. So we're just forming the dot product of the basis vectors evaluated on pairs of features, pairs of inputs, but also kind of modified by the covariance. And then we can just plot this. So this is a plot just like you have in the chapter, so you can see exactly how to make that. And then finally, at the very last step, we use that our equivalent kernel to actually fit our data. So you can see here here's the true function, which is in blue, the data points that we got from it, and then finally the fit. So hopefully that'll give you a chance to kind of play with this a bit and kind of get a handle on it. It sounds like we're going to be talking much more about it in chapter 6, but I think it's a cool idea to flag up now and to kind of get your kind of mind in that space. Good. So I think that was all I wanted to say for today. So let's switch back to So the next section looks like we're going to be changing gears a bit, and I'm talking about kind of a broader topic. So just beyond just like regression, I'm talking about how to do model comparison, model selection, how to kind of do Occam's razor in the Bayesian way. So I think a really important section, which we'll talk about. We might actually split it up into a few sections, but we'll talk about it next time. So thanks for being here. As always, just let me know if you found the video useful. If you have any comments, you thought anything was presented incorrectly, please let me know. I'm happy to address that. And otherwise, let's hope to see you guys next time. Bye.